Hello and welcome to What is Time, Part 1, with yours truly, P. Edward Swan. I'm an expert in the field of information systems. I've been studying information systems for more than 30 years, and today we're going to apply the principles of information systems to explore the subject of time. In this series of videos, we will explore the subject of time by using some very simple and easy to follow examples. We will see how clocks are used to measure time, and we will also find that clocks fail to measure time in a reliable and predictable way. We will observe that clocks are subject to environmental factors that disrupt their functions and cause even the most precise clocks to become desynchronized. We will see how relativistic equations can be used to synchronize clocks when we know the environmental variables that are influencing a clock system. And finally, we will explore some tests that use clocks themselves to detect and measure the environmental influences that every clock is experiencing all the time. What is time? Time is simply the changes that take place in a system. Every object that is known to exist is a system that is experiencing a continuous series of changes or reconfigurations at the most fundamental level, changes that are too numerous for us to count and classify with current technology. We can observe that an old truck gets eaten away by rust as it sits in a scrapyard. We can notice that grass grows. We can observe that the sun shines. Easy, right? But not so fast. How do we measure time? How can we measure all of the tiny changes and reconfigurations that occur in a system? And just as importantly, how can we accurately compare the changes taking place in one system to the changes taking place in another system? So far, the only method that has been developed to measure time is to use a clock as a standard of reference to estimate the changes taking place in a system. So what is a clock? A clock is a machine with a high-energy reservoir on one side and a low-energy reservoir on the other. Examples of a high-energy reservoir include a wound-up spring, a charged battery, a spinning dynamo, which is a generator, and massive objects in a gravitational field, such as water in a water clock or sand in an hourglass. The difference in the energy density between the high and low energy reservoirs causes energy to be pumped through the machine. The clock machine is designed to produce a regular and cyclical pattern over and over again whenever energy is flowing through it. A clock is a regular and repeating oscillator and nothing more. Some examples of systems that produce regular and cyclical patterns include cesium atoms used in atomic clocks, quartz crystals used in quartz watches, and light clocks, which are good for thought experiments. If we count the number of cycles, the regular oscillations produced by a clock, then it gives us a pretty good measure of the changes that are happening in that system compared to other systems. But not so fast, take two. We know that there are changes that take place in a clock system in between the beginning and end of every clock cycle. In other words, every clock cycle is made from a very large set of discrete state changes, tiny steps, that take place to produce that clock cycle. Every part of a clock is made of a giant set of subparts that are constantly in motion. We know that if the mechanical parts of a clock stop working, time is still passing for that clock and for everything else in the universe. Time is the myriad, tiny, relentless, and discrete series of state changes constantly occurring to every object in the universe. And the idea with this picture is that all of the parts of a clock are made of tiny, tiny little subparts. And those parts are made of smaller subparts and so forth and so on until you get to the most basic, simple transactions that are possible within a system. And a clock cycle, which is the only thing that we can read from a clock, is made up of all of these recursive little tiny parts that are packed into these systems, and we can't see those directly. The only thing we can measure from a clock is the major cycles every time something cycles one time around, and we count those: one cycle, two cycles, three cycles, but we don't see all the little tiny parts that are going into every cycle. If a clock produced a list of all the transactions that take place in a system, then that clock would be measuring time. Clocks do not measure all the constant reconfigurations of any system. Therefore, at best, clocks give only an abstract representation of the average changes taking place in a system. There is a relationship between clock cycles and the countless tiny state changes taking place in every system, but this relationship is abstract and not perfectly reliable or predictable. And here is my version of what I believe clocks will be like in the future. They will print out a list of all the little transactions that are happening at the most fundamental level within the system of interest. And every second it will probably print out something like 10 to the 44 transactions. And then the more complicated a system is, of course, it's going to be even way more complicated than that. And tons and tons and tons of transactions are occurring in an endless string. And someday, we may never get there, but the idea is that all the little unary, binary, and ternary transactions that are occurring in a system, which we have no idea what they are, will be determined and printed out by the clocks, and that's what clocks really will be in the future. Right now, clocks are just cyclical oscillators, and there's a relationship between these fundamental transactions in a system and those oscillations, but it's not perfect, and it's not exact, and it's not regular. The cycles of a clock are not perfectly regular or consistent because the relationship between each clock cycle and the fundamental changes taking place in a clock is subject to environmental influences. Clock cycles are affected by environmental factors such as heat, acceleration, and gravitational fields. If we observe two clocks of identical construction as they interact with different environmental factors, those two clocks will almost always produce two different outputs. The two clocks of identical construction will show a variance in the number of clock cycles produced and recorded by each clock. We can observe the behavior of atomic clocks to see how environmental factors affect their clock cycles. Atomic clocks are the most accurate clocks that have been invented so far, though from what I understand, strontium clocks have about 400 times more precision. But even atomic clocks have variations in their clock cycles due to environmental conditions. For example, here's a clip from a video that shows how identical atomic clocks produce different outputs at different places in the gravitational field of the Earth.
Gravity slows time down. As we get closer to the center of the Earth, time slows down. And that's a time dilation effect predicted by Einstein's general relativity.
This isn't the first time scientists have proven Einstein's theory. They have compared clocks on the ground to clocks on airplanes, then to clocks on satellites. The higher clocks went, the faster they ticked.
We have three clocks of identical construction, and they are all producing different outputs: slow, medium, and fast. Now we will ask the question that may be popping up in your mind. Which of these clocks is recording the correct number of cycles? Which clock is producing the correct output? To answer this question, we will observe a different set of two machines that have identical construction. Typewriter A and Typewriter B are two identical, old-fashioned typewriters. Below each typewriter, we can see its output. We notice that the outputs are different. We can ask the same question: which of these typewriters has produced the correct output? Of course, the answer is that both typewriters are correct. The output of any machine is based on the internal state of the machine plus the addition of any environmental inputs. In the case of a typewriter, when the user pushes a key on the typewriter, the user injects new information into the system. The information flows through a mechanical circuit to a type bar that stamps a ribbon to make a mark on a paper. When the user pushes on the key, they inject new information into the machine. We can call this information energy, motion particles, or by any other name we desire. However, what is important to understand is when new information enters the system, that system experiences a change that alters the function of that system, sometimes temporarily and sometimes for a longer duration. Another example of a machine where we can easily observe that the machine will change behavior based on its inputs is a washing machine. A washing machine can take different inputs. If the washing machine has more clothes and more water to process, the cycle takes a little bit longer. If the washing machine has less clothes and less water to process, the cycle is a little bit shorter. Here again, the behavior or output of the machine is not determined by just the machine. We must also account for the temporary information, the clothes and the water, that is part of the system. This temporary information can be called atoms, molecules, energy, or any other name we desire. Nevertheless, we must include the effect of this temporary information when we calculate the output of any machine. Now we can return to the atomic clocks that are producing different outputs. We know that all the clocks are correct. How can we synchronize or reconcile the different outputs produced by these clocks? What is synchronization? Two clocks are synchronized if they always produce the same output whenever they are sampled or read out. If you bring two clocks side by side and they have the same readout, they are synchronized. Two clocks are not synchronized if they show different readouts when they are put side by side. If we can calculate the outputs of any two clocks so that whenever they are brought together they would always agree, then those two clocks are synchronized. Unfortunately, there is no easy way to synchronize two or more clocks. Maintaining the synchronization of any two clocks is a challenging problem that has not yet been solved by modern scientific methods. If these clocks were synchronized, they would always produce the same output, but they do not. As the three clocks are operating in their different environments, we can observe that they do not make any adjustments to compensate for the environmental factors that affect their outputs. Is it theoretically possible to synchronize any two clocks? Fortunately, Einstein's equations give us some mathematical tools that we can use to synchronize clocks. However, to use Einstein's equations, we must constantly detect and adjust for all the environmental factors that a clock is experiencing. There are some simple cases where it is possible to detect and adjust for the environmental factors experienced by a clock, but we need to develop a more comprehensive system before we will be able to synchronize clocks in general. To illustrate this point, imagine that we have two atomic clocks of identical construction, and we take a journey through the solar system, and we take just one of those clocks with us. Before we leave the Earth, both clocks are synchronized to each other by resetting the counters on both clocks to 0. The clock that takes the journey on the spaceship will experience a series of accelerations, velocities, gravitational fields, and other environmental interactions. The clock that remains on Earth will also experience a continuous set of environmental interactions. At the end of the journey, when we return to Earth, it would be very difficult to use Einstein's equations to synchronize the outputs of the two atomic clocks of identical construction. The two clocks would almost certainly show a variance in their outputs even after any attempt to calculate the corrections needed to synchronize the clocks. Given current technology, there would not be enough information about the environmental factors to even start to use relativistic equations to reconcile the behaviors of the two clocks. Please see the link below and join me for What is Time Part 2, where we will continue to explore the difficulties that we face when we try to synchronize any two clocks. In the next video, we will use the principles of information systems to analyze a light clock. We will define a clock cycle in terms of a set of instructions called motion steps, or process steps. By this method, we can identify what causes a moving clock to run slow, and then we can develop some procedures that will help us to synchronize clocks in general. Thank you for watching, and please like this video, share this video, and subscribe to this channel. In my book, Darwin's Machines, you will find a variety of fascinating topics such as time, space, the Big Bang, and free will. If you like science, you will love Darwin's Machines, an information systems approach to understanding the natural world. Please see the links below where you can purchase my book. Also, I am currently working on human longevity technologies so we can all live longer and better lives. Over the last 20 years, I have developed a groundbreaking design for biomedical sensors that will revolutionize the $200 billion per year medical devices market. If you would like to help me bring this product to market, please contact me by email, or you can also support my work by purchasing my books. I am looking for people with all kinds of backgrounds to help me with every aspect of the project, including the technical, organizational, funding, networking, and everything in between. Thank you for your support, and be well.